In lecture 12, which I want to summarize briefly, we want to outline some further, a little bit more intricate points of the preliminary design. We use a concrete bridge again, and that is how to approximate the influence of what we call in German second order. In English we like to use the nonlinear influence. There's also the word P delta effect, which sometimes is used. I say nonlinear influence. What is the increase of the beam moments due to nonlinearity? And the aerodynamic stability of a cable stayed bridge. Both effects only show up in long spans. That's why we use here a very slender cable stayed bridge. We have a main span of 2 times for the full symmetric bridge of 2 times 198 meters. That's nearly 400 meters. And we have a beam, again the same, which is only 1.1 meter high. So we have a slenderness of something like 1 in 350. Well, that shows already up some effects. So what we need for these calculations is the biggest normal force in the beam. You remember we've done that half an hour ago. There is a closed formula to calculate the 36,000 meganewton. Then we need to calculate the elastic supports for the nonlinear influence. That again is the same as I've shown you for the simple example. We have here the different parameter pieces, and we calculate the deflections delta, and from the deflection delta the elastic support C. You know how we do that. I don't go into the figures again. It's all in the script in great detail. Now, the approximation of for the increase, the nonlinear increase of moments works basically on an analogy of a long beam on elastic foundation, which has the buckling load 2 times square root EI. What is called beta here in German nomenclature is our C, what we use for C. And if we then compare, this is just a repeat from an earlier lecture. If we then compare the run of the elastic support with the normal force, we find that if we use the characteristics of elastic support at the tower, near the tower, with the normal force at the tower, then we have the right figures to use with this approximation. And if we then have calculated the buckling load approximately for the whole beam, the true beam stayed compared with a beam on elastic foundations with the same length, then we can use an approximation which is sometimes given to Dischinger, where we say the second order moment is equal to the first order moment 1 minus actual load divided by buckling load. That's a simple approximation, but it helps. So that's our, these are our tools we need. First of all, we calculate the buckling load at the tower. We use the C, the elastic support constant we've calculated. So we find out the buckling load of the whole system is 311 meganewton from the analogy of this beam on elastic support. Okay, then we know the ratio of our actual normal force, which we had calculated here, to the buckling load we have calculated. There's a safety against buckling of 8, that 8.5 exactly. So the increase, very approximate, but it gives us a feeling. The increase, the ratio of second order to first order moment is this 1 minus 1 gamma is 1.13. That means our nonlinear moment increase will be in a maximum, there's the tower, there's a symmetric of 1.13 in the half main span. There's a support at the tower, there's a support at the hold down, there's no increase of second order. There's no normal force in the center of the bridge, so there is no second order. So that will be roughly the run of moments, so we have to increase our life load moments by this amount to take into account approximately the increase, nonlinear increase due to the compression in the beam. And if you go back into the script, you find examples for various bridges there, and something similar. It was higher, it was 1.2 or so. But as a first approximation, it gives you an idea of how this beam under compression, elastically supported, gets increased moment from nonlinear theory. The next one I wanted to outline to you is the aerodynamic, how can we approximately calculate the aerodynamic stability of this beam. Now we go for flutter, and next time I will explain to you exactly what flutter means. I'm not sure whether you are aware of Tacoma Bridge, whether you have seen the movie. I'll show it next time. It's where the bridge beam goes a lot up and down and rotates at the same time. That's a very dangerous phenomenon, one of many, and there's a preliminary way, Klöppel-Thiele developed that in the 60s, how to make an approximate calculation which is not bad compared with wind tunnel test results and so on. Now, our true cross-section is this one, where I gave you originally this approximation, and we have a wind speed to calculate here of 70 meters per second. I'm not going into calculating the bending in the beam from transverse wind. It's all in the script. Basically, we have the beam is loaded by the wind itself, plus the wind which acts on the cables, the lower half. The upper half goes into the tower. I've shown that to you, or you will see it in some detail. I'm not going into that. It gives us some bending moments and stresses. Now, to calculate the aerodynamic stability of a bridge beam, cable stayed bridge beam. It's true for all structures, but I just stick to my cable stayed bridges. We need to know the bending frequency and the torsional frequency. Those are the basic parameters we need to know, plus some others, but which we have to calculate. And thank God it's fairly easy to calculate the eigenfrequency for a cable stayed bridge beam, at least with my simplified methods, but it's not bad compared with the computer calculations. Bending frequency is 0.58 divided by the square root of delta of the beam deflection. And that we can calculate. We've done that several times this morning already. We are looking, if we have this delta under permanent loads, then we know the eigenfrequency in vertical bending. That's very nice and helpful, isn't it? There's only one little trick. We cannot just blindly put the dead load onto the structure. We have to preliminarily sketch the deflection curve, the mode of the first bending frequency. And we have to apply our dead load always in the direction of the first bending mode. That means, okay, in the center it goes down, the dead load goes down, but here it goes up, obviously, so we have to apply the dead load upwards. Don't forget, I've seen many examples where people forgot and then you are slightly out. Okay, we know how to do that. I don't go into the figures. To calculate the deformation in the middle under this load, and it goes on, and we come up, since this, well, not actually occurring load naturally, we have a big deflection here for this 400 meter main span of 6.95 meters downwards. That's not realistic figure, that's a calculation value. And then we know our first bending frequency is 0.22 per second. Well, that's a fairly simple way if you take into account what a precise calculation requires. The second we need is the torsional frequency. Again, in the script there is this approximation formula which basically bases on the assumption that we have two cable planes and the torsional stiffness is provided by the stiffness of the cables. They have to elongate and shorten. The rotational moment of inertia, the rotational stiffness is neglected. That's the approximation. But for our cross-section, it's fair enough. Okay, we can easily calculate, and we come up with a first torsional frequency of 0.29 per second. Now we have then a very vital figure for aerodynamic stability, and that is the ratio of the torsional to the bending frequency, which Thiele calls epsilon. And in this case, it's 1.32. The torsional frequency is only 30% higher than the bending frequency we had here. And then, since we all have a lot of experience with cable-stayed bridges, we say, no good. I tell you here at this moment already, it won't work. We need to be on the safe side, the torsional frequency at double the bending frequency. Then we know already we're in good shape and it will probably work. So what do? Well, we say until now we've had vertical tower legs, which can, in torsion, I have to do it this way, in torsion act independently. If we now use an A tower instead of an H goalpost, we can say, tower, then the two tower tips cannot move independently of one another. And practically for torsion, the tower head is fixed. The elastic elongation of the backstay cable is omitted. Well, if we do that, then calculate the figures, it's all in the script, then we come up with a different deflection and come up with that's wrong. That's with a deflection here. That's right. I have to use this ft square, ft prime, I can say, of 0.71. So we have increased our torsional frequency from 0.29 to 0.71 by using, instead of vertical tower legs, goal post, like a football goal, we have used A towers. I've told you before several times how important these A towers are, and now you see it here in figures how much it works. Now we have an epsilon torsional to bending in the range of 3. I say with 2 it already looks good, so now we are confident it will work. And now we calculate the critical wind. I will explain this. This is a mechanism how the air, how the cross-section sucks energy out of the air. I'll do it in the next lecture. Basically, what it means is that the interaction between the beam and the surrounding air acts like a torsional spring and reduces the torsional frequency down to the bending frequency. And so then this combined can happen. But I'll give that to you in some detail. Right now, we are happy to say that some wise guy found an approximation formula for the very complex, involved, true flutter calculation. And he came up with an approximation formula like this. And if we then use our frequencies and the beam widths and all these constants, radius of inertia and so on, and put the figures into this formula, then we come out with a critical wind speed of 165 meters per second for an airfoil. That means basically for a thin cross-section, a flat slab cross-section. That's how this theory works. And now I have to make the reduction from the airfoil, from the thin flat slab, to my true cross-section here. And that's what we call eta. Now, Thiele have made or evaluated many wind tunnel tests for cross-sections with frequencies and so on, and shapes, and found this relationship. And it's always a little vague, I agree, and you never find exactly what you have. It's a problem. This is shifted. We have the frequency of 3.2. We are somewhere here. So with confidence, we can say, okay, this Thiele diagram, you can go into that and look it for yourself, gives us a reduction factor here, we are somewhere here, of 0.55. So our true cross-section has a critical wind speed of 0.55 times 165 that of an airfoil. So the airfoil with the same characteristics, bending frequencies, mass, widths, and so on, has 165 meters per second critical wind speed. And our true cross-section with the railings, cables, and so on, comes to about 91 meters per second. And we had somewhere earlier, it's in the script, we came up that for this condition, our critical, the wind speed, which say would be given by code or measurements, was 52 meters per second. we can stand 91, so we have a safety in the range of 1.75 against the onset of flutter. And there we can say, well, for a preliminary design, that looks good. Let's be confident in reality later on with detailed calculations and wind tunnel tests. It will also work. Well, thank you very much.